Ampere's law, which is the integral over a closed loop of the dot product between the magnetic field and a differential element along the loop, is equal to the magnetic permeability by the current enclosed in that loop. So essentially, it relates the magnitude of the magnetic field to the current enclosed by a closed imaginary path. And the enclosed path is called the Amperian loop. So consider this wire parallel to the y-axis, and it has some current flowing through it. And we're going to take a closed Amperian loop around this wire. So it's going to be a circular loop, and this circle is parallel to the xz plane in this case. And we know by the right hand rule, if you point your thumb in the direction of the current and curl your fingers, this will give the direction of the magnetic field. So at the top and bottom of the loop, the magnetic field vectors are parallel to the x-axis, and in the middle of the circle, the magnetic field vectors are parallel to the z-axis. And by symmetry, the magnitude of the magnetic field is uniform around this circular loop. So taking our differential vector tangent to this loop, then we can write this as the integral over the closed loop of b by dl cosine theta, which is the definition of the dot product. And if we look at this circle in the xz plane, we have the radius of the circle multiplied by d theta is equal to the length of the differential length vector. So this becomes an integral of b by r d theta. So dl is always in a direction of the magnetic field being tangent to the circle. So cosine theta, being the angle between the two vectors, evaluates to 1. And here we're integrating from theta equals 0 to 2 pi. So the integral evaluates to the magnitude of the magnetic field, which is constant, by 2 pi r. And equating this to the right hand side, we have the magnetic permeability multiplied by the current enclosed in that loop, which is I, and solving for the magnetic field, we get B is the magnetic permeability by the current flowing through the wire on 2 pi r. So recall the messy integral that we evaluated to find the magnetic field near a long, straight current carrying wire using the Biot-Savart law. And here we avoided evaluating that messy integral. So similar to Gauss's law for electric fields, which also helped us to avoid complicated integrals, to obtain the electric field by exploiting the symmetry of the problem. A solenoid is basically a bunch of wire loops wound together into multiple loops. So if you consider the magnetic field due to a single wire loop with the current flowing anti-clockwise, so you can visualize this as the z direction, and this as the y, and this as the x direction. So this loop of wire is parallel to the xz plane. So if the current is going anti-clockwise, by the right hand rule, we see the magnetic field pointing to the right. So note that inside this magnet, you have a higher density of magnetic field lines, because remember that magnetic field lines form closed loops. So by winding these loops of wire together, you essentially end up with a magnet with a north and south pole. And this is an electromagnet because it's created by current flowing through a wire. So here, we assume the solenoid to be very long, with a uniform magnetic field inside the solenoid and a negligible magnetic field outside the solenoid. So therefore we can apply Ampere's law to find the magnetic field inside the long solenoid. So we have the integral of the dot product between the magnetic field vector and the differential length vector around our closed loop is equal to the magnetic permeability by the enclosed current in that loop. So here, it's convenient to choose our Amperian loop to cut through this solenoid in the middle. So it'll be a square loop. So if we travel in the direction of the magnetic field, which can be determined by the right hand rule, as we did for this single loop of wire, we can see the dot product between the magnetic field vectors on this perpendicular edge of the loop and the differential length vectors along these edges of the loop is 0. So the magnetic field lines are essentially perpendicular to this entire edge of the loop. So even a weaker magnetic field at these points is going to be essentially perpendicular to these edges, and we neglect them. So we only have the magnetic field vectors along this edge of our Amperian loop being parallel with the differential length vector. So writing this dot product as the magnitude of B by dl cosine theta, well, dl and the magnetic field vector are parallel, so cosine theta is 1. And then if we integrate this from L equals 0 to the length of this edge of the loop, then we get B by L. And that's equal to the magnetic permeability by the enclosed current. So given this Amperian loop is placed in the middle of the solenoid, then it's only going to cut through these parts of the solenoid. So as we can see, the current travels as follows. So at the top of each loop, we have the current being perpendicular to the face of this loop. So it's essentially flowing through this loop in the x direction. So therefore the total current through the loop is the number of loops multiplied by the current. And therefore the magnitude of the magnetic field is equal to the magnetic permeability by the number of loops on L by I. So we denote the number of loops per unit length as small n. So we replace this term with n. And this is the strength of the magnetic field inside the solenoid. We can use the principle of superposition to determine the net magnetic field at a point in space that's created by various combinations of conductors carrying current, or conducting loops cylinders, and so on. So for example, consider this coaxial cable, which has a solid cylinder carrying a current, IA, directed along the x-axis, and this solid cylinder is surrounded by a thin cylindrical shell carrying current in the opposite direction. And suppose we want to find the current at some point between the solid cylinder and the thin shell, which is at a distance r from the center of the coaxial cable. So applying Ampere's law, which is the integral of the dot product between a magnetic field vector and a differential length vector around the closed Amperian loop, is equal to the magnetic permeability by the enclosed current. So in this case, our Amperian loop will be a closed circle, and as we said, the current is flowing in the x direction, so it's flowing out of the screen. We're looking at this cross section of the cable. So therefore, by the right hand rule, the magnetic field vectors are going to be tangent to this circular path and have a constant magnitude. And the differential length vector along this path is going to be in the same direction as the magnetic field vector. So therefore B dot dl is simply B dl, because cosine of the angle between them is 1. And then we integrate over the length of the entire circle. So we've already seen that because the magnetic field is uniform around the loop, then the integral evaluates to B by 2 pi r. And that's equal to mu naught by the current enclosed in this loop, which is IA. And therefore the magnetic field is equal to mu naught by IA on 2 pi r, where r is less than the radius of the outer cylindrical shell, which will denote RO. Now if we want the magnetic field at some distance r that's outside the outer shell, well, as we said, the outer shell carries a current that's going into the screen, being IB. So applying Ampere's law, by constructing a circular loop outside the outer shell, we have B by 2 pi r is equal to the magnetic permeability by IA minus IB. And dividing through by 2 pi r, we have the magnetic field at a point outside the cable. So this is for r greater than RO. So note that if the current A is greater than the current B, then the magnetic field vectors will be pointing in the anti-clockwise direction and tangent to this Amperian loop. And if IA is equal to IB, then the magnetic field outside the cable is 0. Maxwell's equations are a collection of equations that fully describe electromagnetism. And so far, the first of Maxwell's equations is Gauss's law, which states that the electric flux through a closed surface is equal to the charge enclosed in that surface on the permittivity of free space. And our second equation is the total magnetic flux through a closed surface is equal to 0, because magnetic field lines are closed loops. And the third equation is Faraday's law, which we're going to cover in the next unit, so we'll leave that aside for now. And Maxwell's fourth equation is Ampere's law that we've covered, where we have the integral of the magnetic field over a closed loop is equal to the magnetic permeability by the enclosed current in that loop. So Ampere's law states that magnetic fields can be generated by electric current, and with Maxwell's addition we have the magnetic permeability by the electric permittivity of free space by the change in electric flux with respect to time. So Maxwell's addition states that a changing electric field also creates a magnetic field. And this is similar to a way that a moving charge creates a magnetic field. So remember that the current flowing through this Amperian loop we've seen creates a magnetic field that's tangent to this loop, which we can look at in the XZ plane here using the right hand rule. So we have the magnetic field vectors going in this direction, and if we have electric flux going through this loop also, so remember that electric flux is the integral of the dot product between electric field vector and the differential area that it's going through. So if we have a change in electric flux through that loop, or a changing electric field, then that's going to produce a magnetic field. So note that, for example, if a charge was stationary, then the electric field will be static. So a static electric field does not produce a magnetic field. A sample is placed in a mass spectrometer. And you'll come across mass spectrometers in chemistry, for example. Now cations, being positively charged ions, or you can visualize them as positive charges, are ejected from the sample into an electric field as shown. And the electric field accelerates these ions by a voltage V. So we can write the voltage between two charged plates as the strength of the electric field by the distance between the plates. And here we have the ions treated as starting virtually from rest, because when they're accelerated, their velocities are going to be a lot higher. So we can take V0 as 0, and these ions enter a magnetic field in a spectrograph as shown. And we're told the ions follow a semicircular path before they collide with the spectrograph plate. And in part A, we'll find the velocity when the ion enters the magnetic field. So we can write the electric field as the voltage on the distance between the plates, and therefore the electric force is the charge of the ion by V on D. And that's equal to the mass of the ion by its acceleration. So therefore, the acceleration is QV on MD. So the initial velocity of the ion is assumed 0, being at rest. So the velocity when the ion enters the spectrograph is obtained using this kinematic equation. We have the initial velocity squared plus 2 by the acceleration by the distance between these plates. So the velocity here, after the ion exits the electric field, is constant. So therefore, we have V is the square root of 2qV on m. And the velocity is directed to the right. And in part B, we're asked to verify the ion is deflected downwards. So remember, the magnetic force is the charge by the cross product between the velocity and the magnetic field vector. So here we have the velocity to the right and the magnetic field vectors pointing out of the screen. So the cross product between V and B is going to result in a magnetic force vector pointing downwards. So therefore this force is going to act as a centripetal force that deflects that ion along a circular path downwards. Now in part C, we're asked to find an expression for the mass of the ion. So the magnitude of the magnetic force is QVB, because the velocity and magnetic field vectors are perpendicular. So sine theta will be 1. So the force is the mass of the cation by the centripetal acceleration. So note the magnetic field does not increase the speed of the particle. So the magnitude of the velocity is the same, but only the direction changes. So we have mv squared on the radius of this circular path, which is y on 2. So we end up with 2 on y. And therefore one of these velocities cancels, and we can write this as the mass is equal to qby on 2 times the velocity. So if we substitute for the velocity from part A, we get the square root of 2qv on m. And now we'll square both sides. So we'll get rid of the square root, and 2 becomes 4. And we have q squared by b squared by y squared, and m squared on the other side. And if we multiply through by 1 on m, then m squared on m is m, and we get rid of this m, and we have 4 by 2 is 8. And q squared on q is q. So we end up with 8v in a denominator. Now let's find the time taken for the ion to strike the plate. So the distance that the ion has to traverse is 2 pi by the radius on 2, because we have a semicircular path. So given that the speed around this circle is constant, we have speed is equal to the distance travelled on time. So the distance travelled is equal to pi y on 2. And then rewriting this expression, we get t is d on the speed. So we had the speed from part A, so we can write t is equal to pi y on 2 on v. So we'd get the square root of m on 2qv. And in part E, we're asked to find the work done by the magnetic force. So the magnetic force only causes a change in direction of the ion and doesn't change its speed. So therefore the work done by the magnetic force is 0. A cylindrical conducting rod with a radius r carries a current I with a current density J is equal to 2r. So the current density varies linearly with the radius of the rod. And in part A, we'll find the total current in the rod. So remember that the current is the integral of the dot product between the current density and a differential area that it's going through. So if we cut out a circular section from this rod and take a differential area being an infinitesimally thin ring which has a thickness dr and a radius r, and noting the current is flowing out of the screen, so the current is in a direction of the normal to the cross-sectional area of the rod. So therefore this dot product can be written as J dA cosine theta, which is 1. And now we can substitute for the magnitude of the current density, which is 2r, and the differential area is the circumference, being 2 pi r, by the thickness dr. And we're integrating from r equals 0 to the radius of the section of the rod. So if we take 4 pi being the constants outside the integral, we get the integral of r squared with respect to r, so that will be r cubed on 3, evaluated from 0 to r, and therefore the total current in the rod is 4 pi r cubed on 3. So noting that the current density is in amperes per square meter, so the current will be in amperes per square meter by square meters. So we get the current in amperes. And now we'll find the magnetic field at a point inside the rod. So if we suppose this is the cross section of the rod, then we take our Amperian loop inside the rod at some distance r from the center. So remember Ampere's law, which was the integral of the dot product between a magnetic field and a differential length vector is equal to the magnetic permeability by the enclosed current. So that will be B by 2 pi r is equal to mu naught, and the current enclosed in this loop is obtained using the integral of the dot product between the current density and the differential area, which we did in part A, but instead we would integrate from 0 to r. So what we'd get is the enclosed current in that loop is 4 pi by r cubed on 3. And now if we solve for the strength of the magnetic field, we have the pi's cancelling. 4 on 2 is 2. and dividing through by R, then we get the magnetic field is equal to 2 mu naught by R squared on 3. And by the right hand rule, we know the direction of the magnetic field is tangent to the Amperian loop, going in the anti-clockwise direction, as the current is flowing out of the screen. Now in part C, we'll find a magnetic field at some point outside the rod. So in that case, we take our Amperian loop as a circular loop at some distance r from the center of the rod to a point outside the rod. So again, applying Ampere's law, we have B by 2 pi r is equal to mu naught by the current enclosed in this loop. So we obtain the total current from part A. So that's the total current inside the loop. And again, doing some algebra, we cancel pi, we cancel 2, and then dividing through by R gives the magnetic field is 2 mu naught by R cubed on 3R. So note that for this case, it's for R greater than the radius of the rod, and in part B, we obtain the magnetic field where R is smaller than the radius of the rod.